iterated integrals and the area in the plane, uh, they use the phrase iterated simply to denote that um, the integral that you have is a definite integral. So before in Calculus 1, we talked about definite and indefinite integrals. When they combine um, more than one integral together, and if you're actually evaluating those integrals, they call it an iterated integral. So nothing more than just a definite integral. Here we introduce the idea of a double integral, and then later on we introduce the idea of a triple integral. Ideally, we look at one integral to represent some dimension, one dimension, if you will. And so if we heighten that to two integrals, then we're talking about two dimensions. The idea there would be to solve for the area. Now, you can get the area with a double integral, and you can also get the volume. You would think, okay, triple integral volume, that is the idea. So double integral to try to approximate the area, triple integral to try to approximate the volume. Now, you can get the volume with a double integral because if the integrand itself is a dimension, so then you have two integrals for two dimensions and plus a height from the integrand, and that also would give you the idea of the volume. So we'll talk about all of that in Chapter 14. Chapter 14 sets the foundation for exploring the three classic theorems in analysis, they being the divergence theorem, Green's theorem, and Stokes' theorem. That's our goal. All three try to investigate really one idea, and that is that if I have a mass, is it possible to evaluate the volume of that mass by one, looking at the so-called line integral, measuring the line integral around the particular mass, or a solid, if you will. This path of the line integral could be said some type of neutron or some particle as it moves and rotates around a certain path. It could be several paths, but we just investigate one path. Somebody else may investigate a different path. We could talk about with this particular solid, if this solid, whatever energy that's being exerted on it or from it, if that energy is conservative, then we can talk about the volume of this particular solid as it relates to the energy around this particular path as this particle moves. Green's theorem says I can calculate what's happening with the energy on the whole mass by only investigating what goes on along a particular path. Stokes says that it's possible to look at how a double integral is equal to a triple integral by still investigating this particular solid. So he says I can look at the surface or I can look at the solid and equate both of them. It's a very strange equality, but he makes it work, and we'll look at that. The divergence theorem says that I can look at the so-called divergence, which we hadn't talked about yet, but we will. He can look at the divergence of this particular surface, and then he equates that to either a single integral or a triple integral. So very neat consequences that they all make. All have direct connections to physics, and you talk about the flux integral or the fluid flow along a surface within a tube. That fluid flow, the way it's calculated, is actually still using the triple integral to get the volume. So we look at all of that and see how all that stuff makes sense. But first we need the preliminary, and that is how do we define a double integral? The key to the double integral definition is the region. This region R, we call it capital R. That's the key. What's the key? The region focuses on what's happening in the XY plane. The double integral and the triple integral wants to evaluate the solid that's above the plane. So if I'm standing here in this particular spot, the region only focuses on the space that my shoes take up, just that area. And so the region says that that's so important to this particular solid that we want to make sure that we get the region correct. So where I stand is important, and the space that my feet take up would be important. Now, we can call my height or my weight or my mass, you can call that a certain function f. So I can put that function. There's no function here, this is just the area. I can put a function right there in front of the dy dx, and then I can call that function whatever I want to call it. It can do whatever I want it to do. So this so-called area of the plane region, what's the plane region? The plane region is what's happening in the xy plane. So just look at this in just a minute. Here, this so-called area of the region, the key is R. If R is defined by, we can look at this in two ways. We call the first one vertically simple. We call the second one horizontally simple. We call it vertically simple because I want to bound here x between two vertical lines. And we call the second one horizontally simple when I want to bound y between two horizontal lines. So if it's vertically simple, we say that R is defined by x bounded below and above by a and b. Y is bounded below and above by g sub 1 and g sub 2. G1 and G2 are said to be continuous on the closed interval, AB going back to what bounds X. And so then the area of R is defined with respect to its region, the double integral from first the integral from A to B, and then the second interval from G sub 1 to G sub 2. This dy dx is precise. Dy dx is said to be vertically simple. Watch this. If it's dx dy, horizontally simple. Now that will take us through all of chapter 14 and also chapter 15. So we're going to base this region. Where you stand is important. What is that? That's the foundation, right? If the foundation be destroyed, the psalmist says, then where shall the righteous be? So here, so where we stand, our foundation, it has to be precise. We call it in mathematics, it must be well defined. So now watch this. When you go to integrate, for the first one, for the vertically simple, when you go to integrate, you're going to integrate one integral at a time. You remember back for the partial derivatives, if you had the partial derivative of f with respect to x, you treated y as a constant or coefficient. Well, the same idea for the integration. When I integrate with respect to y, then I'm going to treat my x's as constants or coefficients. Right? So here, wouldn't it be cool if I could just write on the board right here? That would be really nice. You know? So here's what's happening. So the first thing, if it's dy dx, you first integrate with respect to y. Treating x as a constant or coefficient. And then number two, for dx, integrate with respect to x. So secondly, treating y as a constant or coefficient. The same idea for number 2. The dx is first, so I'm going to integrate here first with respect to x. Then I treat y as a constant or coefficient. Then secondly, the dy comes next. Then I integrate with respect to y, treat x as a constant or coefficient. So in terms of how the regions look down on the surface, so if it's vertically simple, look at this first figure, vertically simple. Vertically simple means that I want to bound whatever region that I'm talking about with respect to two vertical lines. Here the line x equal to A, and then the line x equal to B. And then I bound the region above and below by two functions. The below function is g sub 1, and then the above function is g sub 2. So the key that you want to keep in mind, that if it's vertically simple, I want to bound the region by two vertical lines. That's the key. When you're integrating, see how this says the area, the integral is equal, the area is equal to the integral from a to b, and then the integral from g sub 1 to g sub 2. It says dy dx. Here's the key. When you integrate, go over here to the horizontally simple, it's the integral from c to d, and then the integral from h sub 1 to h sub 2. The key is this: when I'm integrating double integral, triple integral, you make sure that the last integral, it looks like this is first, but this is last. The integral that you integrate first is this inside integral. So the last thing you're going to do is this integral out here. Make sure that that integral on the outside has bounded numbers below and above. Notice the integral inside has functions bounded below and above. Here's the thing. If you switch that and you put the functions on the outside of the integral, when you get through with your answer, you're going to have a function and not a number. So here, when you get through integrating, you're going to be evaluating with this last integral, you're going to be evaluating using numbers. C is a number, D is a number, A is a number, B is a number, right? G sub 1, G sub 2, H sub 1, H sub 2, those are functions. So they're on the outside of this last integral. When I get through integrating, then I'm going to be evaluating, putting functions in there. My answer will be a function and not a number. If you're looking for a number like the area or the volume, you want a number. What's the area? Hopefully it's some number, right? What's the volume? Hopefully it's some number. Can we find it? So that's the vertically simple. For the horizontally simple, the horizontally simple says that the region R must be bounded below and above by two horizontal lines. This is y equal to C, and this is y equal to D. And then from the left and the right, bounded by two functions, right? Two functions here that is said to put a boundary on x. X is bounded to the left by h sub 1 of y, and then x is bounded above by h sub 2 of y. Typically, the one that we try to go to integrate is the vertically simple, the dy dx. If it's dy dx, vertically simple. If it's dx dy, horizontally simple. There'll be some problems where they ask you to set up the integration in two ways. Set it up using vertically simple, set it up using horizontally simple. And then they may say, you evaluate using the most convenient or the easiest one. They have those questions out there. Now on my test, I don't go through set it up horizontally or set it up vertically. I just tell you, integrate, find the area. Whichever one you want to use is fine with me, which typically is the vertically simple. Let's look at some problems and I'll show you what I mean. evaluate the iterated integral. So we're going to integrate. This is -1 to 1. Here, since this is dy dx, so first I integrate with respect to y. And then after that, this is for the dy. And then for the dx, integrate with respect to x. So here I first integrate with respect to y, because this is the order. I go to dy first, right? And then after that, and after I evaluate, then secondly, I deal with the dx. So to integrate with respect to y, that means I treat x as a constant or coefficient. Right? So we kind of do the same thing, but it's just a reversal of how you did the partial derivatives, right? So this becomes x squared times y minus y to the third all over 3. Y is evaluated from -2 to 2. Then out here we have dx. Are you with me there? Because you go back, if you were integrating this guy, if you had 5 plus y, and let's say this was dy, wouldn't that be 5y plus y squared over 2 plus c? So here we treat the x squared as a constant with respect to y. So that's why that becomes x squared times y. So now I evaluate. Leave the integral from -1 to 1 there. So I evaluate with respect to y. So this becomes 2x squared minus 8 thirds. That's evaluating at 2. And then it's minus x squared times y, -2. This becomes plus here, this -2 to the third over 3. And then dx. So this is 2x squared minus, this is 8 thirds, and that's the -8 thirds over there. So this is -16 over 3. Well, let me slow down. Just put that 8 thirds. This is plus 2x squared minus 8 over 3. Let's just do it like that. Dx. So this is the integral from -1 to 1. The 2x squared plus 2x squared is 4x squared minus 16 over 3. That's dx. So now, secondly, I integrate with respect to x. So now this is just reduced back to calculus 1 now. So now we're happy. We're happy again. So this is 4x to the third over 3 minus 16 times x over 3. That's evaluated from -1 to 1. We evaluate at 1, so we get 4 thirds minus 16 thirds. And then that becomes minus. We evaluate at the -1, minus 4 thirds times -1 to the third plus 16 over 3 times -1. So this is 4 over 3 minus 16 over 3 plus 4 thirds minus 16 over 3. And so here we get -12 over 3 minus 12 over 3. And so this is -8. Now my question to you is that, did we calculate the area? Is this the area? Mr. Donnie, the answer is contained within his statement. The area was incorporated in that, but this is not the area. Right? So here, no. If you go back to the previous page, the area is defined as this: some double integral, let's say from a to b, integral from g sub 1 of x, g sub 2 of x, and this is dy dx. There's no function here, right? That's the area. So if you go back to this problem, if they did not have the x squared minus y squared, then you're calculating the area. Right. Or it could be horizontally simple, c to d, h sub 1 of y, h sub 2 of y, dx, dy. So here they say what it is. It's an integrated integral. Right? It's not the area. It's not the volume. Right? It's an integrated integral. Integrated integral. Right? We know it can't be the area or a volume because the answer came out to be a negative. Right? All right, let's look at the next one. See if you can do that one. Magic number for this problem is 3. Come up with 3. So, got it? 3. Good job. If we can get 3, man, we're cooking with propane. Everybody got a big plan for the 4th this week? Big plans? No? Yes? Be lazy. Hey. If you can do nothing for a day, man, that's like a blessing too, you know? Oh, man. I look forward to that day. But my wife, the way she tells it, I could never be bored because even when we plan to do nothing, I find something to do, man. You know, I got to go out and work in the yard or something, you know? Yeah. Just can't sit there too long. Yeah. Ryan, did you get 3? Well, you came in late, so yeah, sorry about that. India, you got 3? Yeah. Joshua? You got it. Good job. Did you get it, India? Good. Good. You, hey, everybody got 3. Everybody got 3. All right. So it's integral from 0 to 1. You integrate with respect to x. This is x times y plus y squared over 2. The y is evaluated from 0 to 2 dx. So that becomes the integral from 0 to 1. Replace the y's with 2. So this is 2x plus 4 divided by 2 is 2. Evaluate at 0, you just get 0. Now integrate with respect to x. This is x squared plus 2x, evaluated from 0 to 1. You just get 1 plus 2. You just get 3. Okay. Try your hand at that one. I'll just give the answer. I won't work it out, but let's see if you can get that one. square root of 2 over 4. All right, you should have it by now. So you integrate first with respect to y, because it's dy first, dy dx. Dy goes with this integral, right? And then the dx goes with this guy. So this is first, and then this is second. So you integrate with respect to y. This is y squared over 2 times cosine x. Here the y is evaluated from 0 to 1 dx. This gives you a 1/2 integral from 0 to pi over 4 cosine x dx. You integrate the cosine. This is 1/2 sine x evaluated from 0 to pi over 4. So we evaluate sine at pi over 4. It's the 1/2 sitting there. You know, that's square root of 2 over 2. Then you evaluate the sine x at 0. That's 0. So all you have is the square root of 2 over 4. I don't see what's taking so long. Because, again, the problem just resorts back to calculus 1, right? Just to integrate in a single integral. That's all, you know. So that's the derivative. The derivative of cosine is negative sine. We're integrating. All right. Yeah, we have a lot of problems to work. So here we integrate first with respect to y. So this is the integral from 0 to 1. This is y times the square root of 1 minus x squared. The y is evaluated from 0 to x. Make sure we get that correct. Then dx. So this is the integral from 0 to 1. So here, evaluate the y at x. This is x times the integral of 1 minus x squared dx. You evaluate the y at 0, then the whole integrand becomes 0. So this is all we have here. So now we integrate with respect to x. I have to use my u du substitution, right? Let u equal to 1 minus x squared. This is a direct calculus 1, calculus 2 problem. So we let u equal to 1 minus x squared. That implies that du, yes, is equal to negative 2x dx. I have an x dx sitting out here, so this implies that my x dx can be represented by negative 1/2 du is equal to x dx. So this becomes negative 1/2 times the integral from 0 to 1 of the square root of u du. This is negative 1/2. You can think about this u, I think, better as u to the 1/2 power, right? You look at that to integrate. So this becomes u to the 1/2 plus 1 is 3/2 divided by 3/2. That 1 minus x squared is actually being evaluated from 0 to 1. So we replace the u back with its direct substitution. So this is negative 1/2 divided by 3/2, so the 2 goes upstairs, so this becomes negative 1/3 times 1 minus x squared to the 3/2 power here. It's evaluated from 0 to 1. So that becomes negative 1/3 times 1 minus 1 to the 3/2 minus a negative 1/3 becomes positive 1/3. This is 1 minus 0 to the 3/2. So the first one is 0, and then this is just 1/3. The only thing that you had to remember was that du substitution. Yep. Now I'm going to give you a trick problem. What? You say they're all tricks? Ah! No, no, you're telling the truth. we throw a wrench at you, man. We try to throw you off, man. This next problem is a curve ball problem. It is very easy to work if you see what's happening. Something's going to collapse out, almost like if you remember the theory behind the telescoping for the series, where when you look at those terms, you start adding them up, and all those middle terms cancel out, they collapse. All you have left is the first and the last term, and the last term goes to infinity, so you get the limit of that. So here for this integral, the integral is equal to Riemann's sum, so things begin to cancel out in between. So what happens with this next problem is, don't even think about Riemann's sums, right? That always gave us headaches back in calculus 1 when we had to deal with that. I took the course in graduate school for real analysis, and that's all it was. We first started off with Riemann's sums, and they went to another sum called the so-called Lebesgue measure, which was, boy, make your head scratch. So, see if you can work this one. You see the trick, it's easy. If you don't see it, then you kind of get stuck. So you first integrate with respect to x. This is the integral from 0 to 2, and this becomes 2x over the square root of 4 minus y squared, evaluated from 0 to the square root of 4 minus y squared dy. Replace the x with the square root of 4 minus y squared, so it's just the integral from 0 to 2 2 times the square root of 4 minus y squared all over the square root of 4 minus y squared. Evaluate at 0 for x, you just get 0, so this is dy. So that's the trick there. Those terms cancel out. All you have left is just the integral from 0 to 2 of 2 dy. So that's just 2y evaluated from 0 to 2, just 4. So now, let's see if I can do this and you see how this has worked. First, we integrate I don't think that one is right. Let me come back to that one. Something is fishy about that one. Does anybody have their textbook? Well, I don't know what page it is. It's in the exercise. That's the one there. 24 in the textbook. Huh. Yeah. Let me come back to that one. That's not what I meant for that to be. I don't know why. Let's go to this one. Use an integrated integral to find the area of the region bounded by the graphs of the equations. For these type problems, you need to determine the region. So here, first, you must determine the region. Well, to do that, we need to look at the graph. Examine the graph in the XY plane. Then from here, determine the points of intersection and upper and lower bounds. Okay. So if we look at this graph, this is some parabola with the height at 9, so this guy goes like this. And we know that if we let y equal to 0, why do we do that? Because here this says y equal to 0 and also y equal to 9 minus x squared. So here, if we set 9 minus x squared equal to 0, we can get the points of intersection. Here x is equal to plus or minus 3. So this is negative 3 here, and this is positive 3. So x is bounded by -3 and +3. So here we're looking for our region. So determine this region. We call it R. So R is equal to from -3 less than x less than equal to 3. And then y is bounded below. So look, here's what's happening. Here are those vertical lines. I'm setting this up as vertically simple. I have a vertical line here. I have a vertical line there. X equal to -3, x equal to 3. And then the region, this is the region R, it's bounded, this region is bounded below and above by a lower function, which is y equal to 0, and an upper function, y equal to 9 minus x squared. So here y is bounded below by this y equal to 0, that's the x-axis, less than or equal to y, less than or equal to, that top function is 9 minus x squared. So we set this double integral. I'm looking for the area. It's the integral from -3 to 3. Then it's the integral from 0 to 9 minus x squared. Here this is dy, because look, the y is bounded from 0 to 9 minus x squared. Y is bounded from 0 to 9 minus x squared. So it's dy first. And then secondly, x is bounded from -3 to 3. So this is dx. Right. So I set this up here. We call that the vertically simple. So now we integrate that. So this is -3 to 3. Integrate with respect to y, so it just becomes y, then evaluate it from 0 to 9 minus x squared dx. This is the integral from -3 to 3. Evaluate y at 9 minus x squared, then evaluate y at 0, we just get -0, right, times dx. This is the integral from -3 to 3 of 9 minus x squared dx. So this is just, now it's just straightforward calculus 1 problem. So we integrate with respect to x. This is 9x minus x cubed over 3. Evaluate that from -3 to 3. So I get 9 times 3 minus 3 cubed divided by 3 minus 9 times -3 minus this minus, there's plus the -3 to the third all over 3. So we get 27 minus 9 plus 27 minus 9. All right. What does that give you? 56. Got it. Again, if I scroll back up, this is all they give us for the problem. So what I do is, I look at where it says y equal to and y equal to. I look at those graphs in xy. Right? I set both functions equal because it says y equal to 9 minus x squared, y equal to 0. I set them both equal to find the points of intersection. 9 minus x squared is equal to 0. From there, I found that x is equal to plus or minus 3. So x is bounded below and above by -3 and +3. And then the y is bounded below by the line here, y equal to 0, and then above by that curve, 9 minus x squared. What about the 56? No, this is 27 minus 36. Yeah. Yeah. 18 plus 18. Let's look at another one. Now, I like this problem here because this guy makes you think. Again, use the integrated integral to find the area of the region bounded by the graphs of the equations. So I have x equals 0. So x equals 0 is the y-axis, and then y equals 0 is x-axis. Then I have this curve right here that I say, graphing by hand, how does that guy look? So say I don't know, but I use my tools that I've learned from calculus. So I'm going to get the square root of y by itself. This is 2 minus the square root of x. Square both sides. I get y is equal to 2 minus the square root of x to be squared. So I have this, and I also have y equal to 0. I get that from here. So I set both equal, so that gives me 2 minus the square root of x to be squared is equal to 0. Take the square root of both sides, I get 2 minus the square root of x is equal to 0. That implies that the square root of x is equal to 2. That implies that x is equal to 4. So when y is equal to 0, x is equal to 4. So let's say that's here. Now it also tells me that x is equal to 0. So I find here that point of intersection. So here, let x equal to 0. It tells me I can do that there. So this implies that I have the square root of 0 plus the square root of y is equal to 2. That implies that I get y is equal to 4. So let's say that guy is there. Oh boy. I'm surprised they let me erase it. Last semester it would make a streak and it would just be there and it wouldn't let me correct it. So this guy goes crazy sometimes. This is 4. So here's my problem. My problem, just looking at this y equal to 2 minus the square root of x to be squared, I don't know if this guy is doing this or if it's doing that. Well, it doesn't matter because I can find the endpoints, but it does matter because I want to know exactly how it looks. I mean, you're right. You can still work it without. Well, that just cut out about 5 minutes of what I'm about to do. So oh, man. Thank you, Joshua. Boy. Now, that's an engineer for you, you know, man. We don't care if it does, You don't care if it does this or if it does that. All I know is that I'm trying to find the area of something in there, and we're done. Oh man, mercy, mercy. As my Johnny would say, help us, Father, help us, Father. Well, I want to know, and so because I want to know if the concavity is up or if the concavity is down. I mean, you could do that, but I just use calculus 1. I just use the first derivative test. Yeah. So to find the true nature of y equal to 2 minus the square root of x to be squared, apply the first derivative test. So we have this y equal to 2 minus the square root of x to be squared. This implies that y prime is equal to 2 times 2 minus the square root of x here times the derivative of 2 minus x squared, which is negative 1/2 times x to the negative 1/2. So y prime is equal to this 2 on the outside and that minus 1/2. The 2's cancel. And so I have just a negative in front, 2 minus the square root of x, and that's all over the square root of x. So I set y prime equal to 0. That implies that negative parentheses 2 minus the square root of x is equal to 0. That implies that we get 2 is equal to the square root of x, and we get x is equal to 4. So then I investigate what happens with y prime when x is less than 4, and what happens to y prime when x is greater than 4. And it's less than 4, but it's only going to 0 because the square root of x is only defined for positive values. Y prime is negative 2 plus the square root of x over the square root of x. I'm only checking the sign of the numerator. Here, from 0 to positive infinity, the square root of x is positive, not including 0. So if I take a number less than 4, let's say 1, so I get the square root of 2 plus 1, I get negative, and take a number bigger than the square root of 4, plug that in for the numerator, I get positive. So this guy tells me that to the left side of 4 is slope, huh? Right, exactly. It's sloping down. So basically, you get a minimum at x equal to 4, right? So all I want to know is that it's doing this, right? And it's not, it's not doing that. So if I use the vertically simple, x goes from 0 to 4, and like Joshua said, it doesn't matter because that curve, whether it's curving, oh, it's the eraser. If it's curving down or if it's curving up, it's still above y equal to 0. So but it's just good to know, I think. So the region here is x is going from 0 to 4. And then y is bounded below by y equal to 0, and then above by that curve there that we got, 2 minus the square root of x to be squared. 0 less than or equal to y less than or equal to 2 minus the square root of x to be squared. So then we compute our area based on that. This is the integral from 0 to 4, then this is the integral from 0 to 2 minus the square root of x all to be squared. And this is dy dx. So integrate with respect to the y, we get y evaluated from 0 to 2 minus the square root of x to be squared, dx on the outside. So this just becomes the integral from 0 to 4 of 2 minus the square root of x to be squared dx. We just simplify here this term that's squared. So this is 4 minus 4 times x to the 1/2. We set that up for integrating. And then plus x. So now we integrate. Get 4x minus 4 times x to the 1/2 rate plus 1. That's the 3/2 power divided by 3/2 plus x squared over 2. So we simplify that. This is 4x minus, looks like 8/3 times x to the 3/2 power plus x squared over 2. Evaluate those x's from 0 to 4. So we get 4 times 4 minus 8 over 3. This is 2 to the 2nd to the 3/2 power plus 4 to the 2nd all over 2. I looked at that 4 as being 2 to the 2nd so that these 2's would cancel out. So 16 minus 8 over 3, this becomes 2 to the 3rd, plus 16 divided by 2 is 8. So 24 minus, this is 8 times 8, 64 over 3. And you calculate that out. What do you get? 8/3? That's exactly right. That's the area. Now remember again how the area is defined. If I scroll back up a little bit, see the area is equal to 2 integrals, and then it's just dy dx or dx dy. There's no function right here. All right. Now this one here is not as cumbersome in terms of the graph, like how this guy was. We have to determine if this guy was sloping downward or upward. But look at this next one. I think it's interesting too. See what you can do with that one. you get the graphs for those? Yep, it's parabola going up, and then you got this slanted line. Yeah, so that slanted line is the function below, and then that parabola is the function above. Set both of the equations equal, and you can find the intersection for the bounds for x. So you get x is bounded below and above by what two numbers? -2 and 1. Yeah, exactly. Sounds like 9/2. Let's see if you got the right setup. So if we look at the graphs, well, let's see. This is 4 minus x squared is equal to x plus 2. Look for the points of intersection. So this implies that if I get everything on the right side, 0 is equal to x is bounded below and above by 1 and negative 2. Is bounded below by this line, see there, so x plus 2 plus the y, and then above by the curve, 4 minus x squared. You definitely need the right region to be able to calculate the area, because the area is based on that region, so that's most important. Do this, you integrate with respect to y, you get y evaluated from below and above. That just becomes 4 minus x squared minus x minus 2. Can I do that? Is that okay? Is everybody with me there? Just skip the step. You know, back when we were in school, you get upset with the teacher. She said, skip steps. Never liked the teacher that skipped steps, especially in math. So this is the integral from negative 2 to 1. That's 4 minus 2. That's 2 minus x squared minus x dx. And so integrate with respect to x. This is 2x minus x squared over, that's x squared, x cubed over 3. This is the minus the x squared over 2. That's evaluated from negative 2, to 1. So we evaluate at 1, we get 2 times 1 minus 1 to the third over 3 minus 1 over 2, 1 to the second over 2. Then minus 2 times negative 2 minus this minus is plus the negative 2 to the third over 3 plus negative 2 squared over 2. So this is 2 minus a third minus a half plus 4 minus 8 thirds plus 2. So the 2 and 4 and this 2 is 8, and we have the minus 1/3 minus 8 thirds is minus 9 thirds, so just minus 3, and that's minus a half, so it's just 5 minus 1 over 2, 9 over 2. Okay. Is everybody happy with that? All right. I got 2 problems left to do. I'm going to work those, and then I'm going to toggle back to a problem, and I'm going to let you work as a group assignment. So the last 2 problems consider the idea that if you sketch the region R, they give you this double integral. They want you to basically, from the double integral, look at the region. What is x bounded by? What is y bounded by? Then change the order of integration and show that both orders yield the same area. So look at vertically simple, then look at horizontally simple. Calculate both. You should get the same thing. So if I look at this, this says that x is bounded from, you see that, 0 to 1? That goes with the dx, right? And then here, y is bounded from 0 to 2. This becomes our region. Now, if I calculate that as it is, this is the integral from 0 to 1. This becomes y evaluated from 0 to 2 dx. And so that just becomes the integral from 0 to 1 of 2 dx. This is 2x evaluated from 0 to 1, and we just get 2. Now, since x and y are both bounded below and above by numbers, they're fixed, changing the order of integration, simply you just switch it directly, and that's fine. If it's a function, I'll show you for the next problem, you have to kind of do some work when you switch the order of integration. It's not as easy and direct as we would think. So if we change the order of integration, we get the integral from 0 to 2, the integral from 0 to 1. This is dx dy. Well, we would love that if that was always the case, but it's not. So we integrate 0 to 2, then this becomes x evaluated from 0 to 1 dy. This is just the integral from 0 to 2 of 1 dy. This becomes x evaluated from 0 to 2. Here we just get 2. I'm going to show you in the next problem where switching that order is not as easy as we would hope it to be if I have the boundary and the boundaries are functions. Here my boundaries were fixed numbers, 0, 1, 0, 2, right? So just switch that directly and you're fine. So here, switch the region R, sketch the region R whose area is given by the iterated integral, then change the order of integration and show that both orders yield the same area. So let's look at this region. So this tells us that y is bounded from 0 to 1, and then x is bounded below by the negative square root of 1 minus y squared less than or equal to x less than or equal to above by the square root of 1 minus y squared. I was erasing. Just going to leave that alone. Let's see how this guy looks. This is x equal to the square root of 1 minus y squared and x equal to negative square root of 1 minus y squared. If I just take one of these guys, square both sides, I get x squared is equal to 1 minus y squared. This implies that this is x squared plus y squared is equal to 1. Basically, the whole graph would be a circle with radius 1. Okay. So, circle with radius 1. But this region R is not the circle. It's the top part of the circle. Let's see. It says x is going from negative the square root of 1 minus y squared. That's this guy. It's really what's happening down here too. So this, oh, I don't know why is it doing this. Mercy. Okay, let's see. Maybe just keep it at black and just let that, don't change the colors anymore. So what I was going to put here was, this is negative the square root of 1 minus y squared. Then you come over here. It's this whole right side is the square root of 1 minus y squared. What makes it the top part? Because y goes from 0 to 1. I'm going to change it to this just for this time. This is y equal to 0. And then here is y equal to 1. If it was y goes from negative 1 to 1, it's the whole circle. But y goes from 0 to 1. So it's just the top part of that sphere, or the top part of the circle. So we're going to integrate the way they give it to us first. Not green. Even though that does look pretty. 0 to 1, integrate from negative the square root of 1 minus y squared, the integral from the square root of 1 minus y squared. And this is dx dy. This becomes the integral from 0 to 1 of x evaluated from negative the square root of 1 minus y squared that goes to the square root of 1 minus y squared. And then this is dy sitting there. So this area is equal to the integral from 0 to 1. This is evaluate x at the square root of 1 minus y squared. Then this is minus, that minus becomes plus the square root of 1 minus y squared. And this is dy. This is 2 times the integral from 0 to 1 of the square root of 1 minus y squared dy. Need to integrate this guy. I resort back to using trig substitution. That 1 minus y squared was for the trig substitution for let sine equal to, right? So let sine u equal to y over 1. So if that's the case, we have that right triangle. Here's some angle u. Let sine equal to y over 1. So y is the opposite over 1, the hypotenuse. If you calculate using Pythagoras' theorem, this leg here would be the square root of 1 minus y squared. Well, the integrand involves two things. It involves the square root and it also involves the dy. So to get dy, we just take, and this is not a t, looks like a t, y over t, Mr. T. Mr. T was pretty cool. We have sine u is equal to y. Take the derivative here. This is cosine u du is equal to dy. So this dy here would be represented by the cosine u du. Cosine c. Oops. Now to get this radical, I need to involve this leg over here. Well, we can use cosine. So cosine u is equal to the adjacent over the hypotenuse. So that's just the square root of 1 minus y squared. So we get it. So here I have 2 times the integral from 0 to 1 of the square root of 1 minus y squared dy. So this is 2 times the integral from 0 to 1. Here this square root is cosine u, and then dy, this dy is cosine u du. So this is 2 times the integral from 0 to 1 cosine squared u du. And then there was another section in Calculus 2 that said that if I ran across the integral of cosine square by itself, I convert the cosine square to a double angle representation, right? So this is 2 times the integral from 0 to 1 of 1 plus cosine 2u all over 2 du. Okay. If it was sine square u by itself, that's converted to 1 minus cosine 2u all over 2. Right? Now, I tell you, there's not too many things that I remember from trigonometry. Like I said, it's a handful. The handful that I remember that I know that I always see in calculus 1, 2, and 3, differential equations. This guy is one of them. So trig, recall, the one was that equilateral triangle that I gave you before. This was 2, 1, the square root of 3. Power over 3. Power over 6. The second thing that I remember from trig, take a square with all sides equal to 1, bisect this guy, use Pythagoras, we get the square root of 2, and this is theta is equal to power over 4. The third thing that I think is important from trig, cosine square x is equal to 1 plus cosine 2x over 2, and what goes with that, sine square x is equal to 1 minus cosine 2x, oops, too far. fourth thing that is sine 2x is equal to 2 times cosine x sine x. In terms of memorization, those are the 4 things that I've just remembered, and if you keep those, then you're good to go with all of calculus 3, even differential equations. Let me finish this problem, just half of it. This guy came out to be 2 times this is 2 divided by 2. That cancels out. I'm here. So the 2 goes out. So this is just 1 plus cosine 2u du. I think this is going from 0 to 1. Yes. So this becomes u plus sine 2u over 2. Evaluate that from 0 to 1. You have to use a u du there. There's 2u, so you get that 1/2 downstairs. But u, this u becomes sine inverse of y. So this is sine inverse of y plus the cosine 2u, I use this guy, so that becomes 2 cosine u sine u. So this is sine inverse of y plus 2 times the cosine from the right triangle was the square root of 1 minus y squared. So this is 2 times the square root of 1 minus y squared. And then the sine u was just set to equal to y. Sine u is equal to y. This is times y. Now the y is evaluated from 0 to 1. That's a 2 there. So this is sine inverse of 1 plus 2 times the square root of 1 minus 1 times 1, then minus sine inverse of 0 plus 2 times the square root of 1 minus 0 times 0. So all we have is sine inverse of 1 minus sine inverse of 0. Now this sine inverse of 1, because I keep nothing in my head, set this guy to equal to, let's say, x. This implies that sine x is equal to 1. When is sine equal to 1? Here x is power over 2. For that next one, set sine inverse of 0 equal to x. This implies that sine x is equal to 0. That's when x is equal to 0. So our answer is power over 2. Now look, does that make sense with algebra and basic trig? Here, if I have a circle, and I'm looking for its area, half of it, right? This is half of a circle. Well, I know that the formula for the area for a circle is pi r squared. So this is times pi, and r is equal to 1 squared, so you get pi over 2. Thank you. So it'd be good if they say, you can use trig to work this problem. You get the answer just like that, right? So, thank you.